Okay, this morning we start linear algebra. Okay, so I'm going to start with something that's hopefully a little bit familiar to you, and that is systems of linear equations. Okay, so let's take an example. So let's suppose we have x plus 3y plus 4z is equal to 3, and 2x plus y, is that plus y? Oh no, so I want to do exactly the same equations I have here. So this is a minus y and minus 2z, and this is equal to 3 also, and minus x plus 4y plus z is equal to minus 5. Okay. So here's a system of linear equations that you perhaps recognize. Okay? And this can be written as the matrix system. And the matrix system would be, well, we put the coefficients in this matrix, so we have 1, 3, 4, okay, to multiply x, y, and z, and that's equal to, the first one is 3, okay, and then the next equation is 2 minus 1 minus 2 is equal to 3. Some people put these equal signs at the top, some people put them in the middle, doesn't really matter, right? And then the last equation is minus 1, 4, and 1, and this is equal to minus 5. Okay? Or we can write it as a so-called augmented system. And the augmented system would be, I'm sorry I haven't lined this up, but essentially this is the same. So I'm going to take the numbers from the matrix, and I'm going to augment, and I'll just put a little dashed line in here. That's of no consequence. It's just to help you read this. And we put the 3 at the side here. So in some sense, we've lost the x and the y and the z. Please tell me if I make a mistake, right? As far as I can see, that's the same augmented system. Okay. Okay, so if we have such a system of equations, then we can manipulate them in certain ways. So, okay. So tell me if this pen is too thin, because I can't find a thicker one. So there are 3 types. Can you read that? Can we read that? I'm asking the people on the back row, really. Yeah. Okay. Okay, there are 3 types of elementary row operations. So people, I'm not going to write this all the time, so I'm going to call this an ERO, an elementary row operation. And they that do not change the solution set. Okay. So the first elementary row operation I'll call A is to swap any two equations. And the equations correspond, of course, to rows, as you've seen in this matrix. So I can swap them. In other words, those equations I was given at the top, I could have been given the second one first. The first one third. So no change in the solution set if I simply take them in a different order. They're the same equations. EROB is to multiply any equation. And the equations, as you know, are the same as rows. Any equation or row, by a non-zero scalar. Okay. So if my second equation there was 4x minus 2y minus 4z equals 6, it would carry essentially the same information. C. Okay. And C is add a multiple of any equation or row to another equation or row, any other. So these are our three elementary row operations. So let me do an example as above. So this is exactly those equations there. Okay. So I start off with the augmented matrix 1, 3, 4, and then there's this little partition. And I augment it by 3. And then the second equation is 2 and minus 1 and minus 2. And that gives us 3. And the final equation is minus 1 and 4 and 1. And that gives us minus 5. Okay, so now I'm going to apply elementary row operations. All right. So the first thing I'm going to do is I'm going to subtract twice the first equation from the second equation. So I'm going to leave the first equation alone, so this will be the same. 1, 3, 4, partition 3. But I'm going to, I need to leave myself space to tell you what I'm doing, so I'll leave some space. So I'm going to leave some space for what I'm doing. So here we go. So 1, 3, 4, the partition and the 3. And then I'm going to do row 2 becomes row 2, plus minus 2. I'm going to move this again because there's still not enough room, times row 1. So the first row stays the same. And now if I I add minus 2 times the first row to the second row, I'm going to create a 0 there, aren't I? Because 2 plus minus 2 times 1 is 0. And then I've got to take minus 1 and add minus 2 times 3 to it. That's minus 6. That gives me minus 7, as far as I can see. And again, minus 2 lots of this gives me minus 10, I think. And then 3 minus 2 lots of 3 is minus 3. Okay? So all that I've done is somehow make this simple. And then I'm going to do the same sort of thing in the final row. So row 3 is going to be row 3 plus what? Plus 1 times row 1. Okay, because then if I add minus 1 to 1, I get 0. So this is just this elementary operation, C. Right? That's all this is. And so 4 plus minus 1 is 3. And 1 plus minus 2 is minus 1, as far as I can see. What? Oh, I'm adding the wrong row. I'm adding the wrong row. Look at that. Okay. I've got to add 4 to 3 to give me 7, because I'm adding row 1 here, and 1 to 4 to give me 5. Is that right? That seems reasonable. Okay. And then minus 5 add 2, add 3 is minus 2. Okay. So that's just using this elementary operation. I've done 2 of them at the same time because this one doesn't affect row 3 and this one doesn't affect row 2, so I can do them at the same time. And then what I'm going to do is I'm going to add row 3 to row 2. All right? And so this carries on to, if you like, okay, I'm going to do row 3 becomes, that's what this means, right? Row 3 plus 1 times row 2. And what's that going to give me? Well, the first equations are going to be the same. And now the second equation is not going to change. So this is 0, minus 7, minus 10. And I get minus 3. But now I add this to this to get that, well, fortunately, 0 plus any multiple of 0 is 0. Right? And this gives me a 0 here by adding row 2 and row 1. And if I add these two together, I should get, I guess, I should get minus 5. And these two together, I should get minus 5. Okay. Okay. All right, so what have we achieved? We've achieved that x doesn't appear in this equation, and x nor y appear in this equation. All right, so what we achieved is that so that now the matrix is upper triangular, by which I mean it has zeros below its diagonal. Right? Okay. Okay. Thus, the original equations are equivalent to, in other words, equivalent means I have the same solution set as, that's what equivalent means here, okay, and these equations are now x plus 3y plus 4z is equal to 3 minus 7y minus 10z is equal to minus 3 and minus 5z is equal to minus 5. Okay. So I'm going to call these 1, 2, and 3, which I've not labeled so far. Okay. And immediately you can see from equation 3, what does this tell us? This tells us that z is equal to 1. right? And so 2 becomes minus 7y, minus 7 times y is equal to minus 3 plus 10 lots of 1. That is, I've simply moved that term, now that I know what z is, onto the other side. And minus 3 plus 10 is minus 7, isn't it? Oh, minus 7. Plus 7, right? Minus 3 plus 10 is plus 7. Okay. And then also 1 becomes, equation 1 becomes x is equal to 3, that's this guy, minus 3 lots of y, well, we know what y is now minus 1 by the look of things, right? Minus 7y equals 7. And so 3 minus 3 lots of minus 1 minus 4 lots of what z was, and z was 1. And so this is equal to 2. Okay. This process is called backwards substitution. Okay. And now we finally got the solution set. So the solution set, well, the solution here, okay, the solution set for this system is unique. Okay. Okay. And is x is 2, y is minus 1, and z is 1. Okay, so this process of systematically reducing, I could say, reducing a matrix to upper triangular form using E, R, O, C, okay, what we call C over there, is called Gauss or Gaussian. You've all heard of Gauss, right? Gauss or Gaussian, I call it Gauss or Gaussian elimination. Okay. Okay, so all you've done is you've systematically introduced zeros into the lower triangle. And that's your Gaussian elimination. And it's clearly one way of finding a solution set here. No question about that, and that's what we've done. Okay, so one could continue. Okay. The application of EROs. Elementary row operations, okay, to get a diagonal form. Okay, so what happens there? We start off with what we have, the upper triangular form, which is, shall I take it from here? 1, 3, 4, and 3, 0, minus 7, this is 0, not 6, minus 10, and minus 3, and 0, and 0, and minus 5, and minus 5. Okay. And what can I do now? I can do the following. I can say row 1 becomes row 1, okay, plus 4/5 of row 3. Okay, so if I do that, then I get, well, the first row becomes 1 because 4/5 of 0 add to 1 doesn't change it clearly. I get 3 similarly because 4/5 of 0 add to 3 doesn't change it. But 4/5 of minus 5 add to 4 gives me a 0 here. Okay? And the right-hand side becomes, in fact, minus 1. And I'm also at the same time going to do row 2 becomes row 2, okay, plus, what am I going to do here? It looks like minus 2 lots of row 3. So if I add this, minus 2 lots of this to this, I should get 0. So again, I get 0 and 7 and 0, and the right-hand side becomes 7, and the last,
The first one should be minus 7.
minus 7, thank you very much. All right. Didn't change it because I added 0 times here. And the last row becomes 0. Well, it stays as it was, 0, 0, minus 5, and minus 5. So now we just have to add some multiple of this to this to make a 0. So if we again carry on, and then we have row 1 becomes row 1 plus, and this is 3/7, isn't it, of row 2. And if we get 3/7 of row 2, then this gives us the following matrix. I should say this here. Right. Gives us the following. 1, because again this doesn't change. This becomes a 0 now, that's the 3/7. Fortunately, this doesn't change. You can see why we use row 2, right? So, well, sorry, this is a 1, what I'm saying. And then this is 0, and then this is minus, and this becomes 2. Okay, 3/7 of this, so on. And then the second row is 0, and minus 7, and 0, and 7. And the final row is 0, and 0, and minus 5, and minus 5. And I'm going to give this a label. So my labels are altogether local. So today's label plus is this equation. Okay, if I write plus tomorrow, it means whatever equation I say tomorrow. Okay? And you can see from here the solution set, from which the same, I shall say, of course it should be, solution set. Okay, so you can actually get a diagonal form if you wish to. This, and here's an interesting verb you've perhaps never heard of before, this zeroing, okay, so this is the participle of the verb to zero. This zeroing of the upper triangle okay, is called, it's also named after Gauss, so Gauss and also Jordan. So in English, Gauss-Jordan elimination. Okay. So it depends what your purposes are. whether you want to do Gauss elimination or whether you want to do Gauss-Jordan elimination. Okay. But you can see what I've done, right? And this example shows you exactly how you do this, right? And you can see why I took here the multiples of row 3, because I've got these two zeros. So by doing these two zeros, I don't change anything in these first two columns, right? And then here I use row 2 because I don't want to reintroduce something into the third position, right? So this is the systematic treatment of this thing, right? Okay. So the equations plus here can be put, so the equations plus, okay, can be put into a reduced row echelon, okay, form. It's clearly a mouthful even for me, so I'm not going to call it that. I'm going to call it RE, reduced row echelon form, okay, in which the leading entries, or the leading non-zero entries, okay, are 1, okay, I should say in every row. Okay, the number 1 by using EROB. In other words, it's quite clear you can scale, right? And I'll just do this very briefly, and then I'll stop. Then I'm done with this. So I've got 1, 0, 0, 2. That's already in reduced row echelon form, so I don't need to do anything with that. 0, minus 7, 0, 7. Okay, and I've got 0, 0, minus 5, minus 5. And all I'm going to do is I'm going to do scaling. Row 1 becomes row 1 times, or becomes 1 times row 1. This is obviously a sort of irrelevant thing to do, right? Because I'm already in row echelon form. Reduced row echelon form, that's this. Okay. And then the second one is obviously not so trivial. Row 2 becomes minus 1/7 of row 2, which gives us 0, 1, 0, minus 1. And row 3 becomes row minus a fifth. Minus a fifth times row 3. It gives us 0, 0, 1. And this becomes, what does it become now? It becomes 2. 1? Oh, of course, of course. There you go. You see that I'm not very good at arithmetic, but that's fine. Don't mind that. Good. You're all that are. That's very good. You're good at arithmetic. So this is our reduced row echelon form. And again, you can very clearly see that this is now the solution. Okay, so sometimes this so-called triangular form, right, what I've called upper triangular, sometimes that's called row echelon form. And this is reduced row echelon form. But you'll see these different words at different places and at different times. Okay. So this is all we needed to do. Gauss elimination to find the solution in this case. We could go further and use Gauss-Jordan elimination to find this form, which is in row echelon form, right? This is row echelon form, as I say. Okay. And this is, sorry, I must get this right. And this is the reduced row echelon form. This is the one I'm going to talk about a little bit later, and this is the form that is used quite a lot in the problem sheets. So you'll see this. Okay. I'm just showing you how you can do this. Now you might say, well, okay, why did I put up 3 EROs? I've only ever used this one, and then finally I've used this one to get myself to reduced row echelon form. And is A ever used? And let me just say that EROA, okay, is only necessary. Oh, okay. If A0 prevents, okay, Gauss elimination. Okay, so for example, if you have the equation simply 0, 1, partition 1, and 2, 3, partition 5. If you have this situation, then you can't do Gauss elimination because there's no multiple of this equation you can add to this one to make a 0 in this position, right? But that's not a problem, so what do? You just swap. Right. That's EROA. Right. You swap the 2 equations. And then it's already in upper triangular form. I'm sorry, I've been wrong here. This is, I should be a little bit careful with my nomenclature. It's not a nomenclature I'm going to use. I think upper triangular, lower triangular, and so on is easier, but this isn't row echelon form, I'm sorry. The row echelon form is precisely this form, right? The upper triangular form. Okay, this is row echelon form here. Oh. There. What I call upper triangle. Okay. Just to show you that you don't have to have such trivial examples as this. If you have, for example, -1, 2, 1, and something, doesn't really matter, 2 and 4, -4 and 2, and 1 and 5 and 2, and it doesn't matter what you have here. Okay, this will then go to, if you do Gauss elimination, you go -1, 2, 1, something on the right-hand side, and then it will go to, well, 0, and in this case, I think 4. And then 1 and 5. 0 and, sorry, I've done the elimination here. 0 and 7 and 3, and something on the right-hand side here. It doesn't matter what these numbers are here. And again, I can't do, if I do Gauss elimination there, that's exactly what I get, because unfortunately, add 2 to that, and you add 2 of that to that, you get 2 zeros. And now I can't do Gauss elimination because I can't take a multiple of this row to add to this row to put a 0 in this position. And so what do? I just swap these 2 rows. So this is EROA. Okay? Otherwise, Gauss elimination, and I perhaps should have said that's what this is. Right? Gauss elimination. I shall call it GE. And GJ, which I have said, Gauss-Jordan, okay, are systematic procedures. In other words, I can give them to a machine or a monkey to do these calculations. Right. Okay. All right, so I've just done that example so far. And that's sort of like what you've already seen, I guess. Perhaps some of you. I'm just solving a system of equations and I'm being a little bit pedantic about it. And I'm not going to apologize for being a little pedantic about how I solve them. That is, you as humans try to use your intuition and to make your life a little easier. I I'm trying to do something that's entirely systematic. Right. Okay, here's another example. Okay, so this one is going to be 2w plus 3x plus 4y plus z is equal to 1. And w minus x minus y plus z is equal to 1. And, oh, and I'm sorry, I'm going on to the next board. That's fine. It's still 3 equations. 4w plus x plus 2y plus 3z is equal to, and I'm going to put in a parameter here. Let's call it alpha. Okay? So now we can write this as an augmented system quite easily. This is 2, 3, 4, 1, partition 1, and 1, minus 1, minus 1, 1, partition 1, and 4, minus 1, minus 1, 1. Oh no, I'm writing down the same equation, sorry. This is the problem of being too close to the board. You can see it, I can hardly see the board. 4, so this equation I'm writing down, plus 1, right? Plus 2, and plus 3. That's this one here, and then there's an alpha down there. Okay, so here's another augmented system for this set of equations, and I'm now going to do Gauss elimination, okay? And Gauss elimination is going to not change the first one as before. And then the second one, I'm going to take a half of the first equation from this equation to make 0 here, right? And so on, and that will give me 0, and I'm just going to write down the numbers. And you can do the arithmetic, and you can tell me if these numbers are correct. I believe they are. This is a half. And then I'm going to take twice that row from that row, and I'm going to get a 0 there. And then I get these numbers, I think. I get 0, minus 5, minus 6, 1, and alpha minus 2. That's the first stage of Gauss elimination. And then I'm going to do the next stage, and the next stage of Gauss elimination is not going to change the first equation, nor the second equation. But the final equation is going to become, I've got to add twice that to that, and I'm going to get 0, 0, because 0 is plus 0 is 0. And if I add twice that to that, okay, have I got this right? Yes, I think I've got this right. It looks like that must also be a 0. Okay, sorry, I'm going to subtract twice that. And minus 2 times that and add to that. Minus 2 times that and add to that. And the last equation is, oh, minus 2 times that and add to that is also 0. And then what do I get in the right-hand side? I get alpha minus 3. So I've just done Gauss elimination. And these are my equations for today, which I will call star. Okay? So first of all, if alpha is equal to 3, okay, then y and z, okay, can take any value. Okay. So I'm going to parameterize, okay? I'm going to parameterize. I'm going to say put y is equal to s and z is equal to t. Okay. And then, okay, what do I get? I get that minus 5 over 2 lots of x is equal to a half plus 3 lots of s minus a half lot of t.
Minus 3s?
No, it's plus 3. I think there's a minus sign here. Right. And so this tells me that x is equal to minus a fifth minus 6 over 5 lots of s plus 1 over 5 lots of t. Okay. And I can also write down then w. Well, at least I've got 2w. 2w is equal to 1 minus 3 lots of x. And now I know what x is. X is equal to minus 1 over 5 minus 6 over 5s plus 1 over 5t minus 4 lots of s minus 1 lot of t. Okay. And so this gives w in terms of s and t. And you can simplify it, but it's clearly giving me w in terms of s and t. Okay? So now I can write down the result. The result is that w, make sure I've got enough space here, w and x and y and z is equal to, and then it looks like it's 4/5. Okay. Because this is 1 plus 3/5, that's 8/5, and you've got to divide by 2. Minus a fifth. Oh, that's this guy here. And 0 plus s times the vector minus 11 over 5 minus 6 over 5 and 1 and 0. So this just says y is equal to s at this stage. Plus t times, and then the appropriate numbers are minus 13 over 10. You can check these things for yourself if you can't do them in your head like I can't at the moment. And 0 and 1. So this last equation says z is equal to t. Okay. So this is a two-dimensional, okay, plane in four-dimensional real space. You want to think of geometrically what this point means. I'm in four-dimensional space, and I can go to a particular point, and then I have to go any distance in another direction, plus any distance in another direction. So I go to a point, and I can go that way or that way. So that fills out a plane for me. Okay? So that's what happens. Clearly my parameterization by s and t is sort of unnecessary, but explicitly done here to make it a little bit easier for you to see it. If it does, I could clearly have called this y, and I could have called this z. That's exactly what they are, right? Anyway, that's fine. I just introduced things that you might think would be parameters. Now, I'm going to carry on here, in danger of breaking my rule of making sure you guys can see, because I want you to see this follows on. I'm not going to just, if I jump over there, you're going to think, oh, there's a discontinuity, and I don't want that to happen. So the question is if, okay, Okay, so first of all I should say these equations are consistent, okay, and have infinitely many solutions. Oh. Some people would say doubly infinite, because there's two parameters, s and t, you can choose, but certainly infinite. Okay. On the other hand, if alpha is not equal to 3, remember all of this is predicated on if alpha was 3, then all this follows. But if alpha is not 3, okay, the last equation is, well, take it from equation star there, it's 0 times w plus 0 times x plus 0 times y plus 0 times z is equal to alpha minus 3, and alpha minus 3 is then not 0 if alpha is not 3. And what's the solution of that? Sorry? There isn't one. Right. There is no solution, of course. Okay. And so this is not possible for any choice of the variables. So this is not possible for any x, w, x, y, and z, so no solution exists. In other words, the solution set is the empty set. Okay? These equations are inconsistent. Okay? These equations are inconsistent. Okay. I'm now going to make some notes. It is the same example, but I do want to observe my rule a little bit here. So note that star, there's still only one star on the board, and that's that equation over there, so that must be star. Okay, so star is in row echelon form. Okay. Reduced row echelon form, okay, can be achieved by using EROC to create a 0 in the 1-2 entry as in Gauss-Jordan elimination. Okay. And then applying ERO B. That is just scaling the equation. So all I'm saying is that if you take these equations star here, you can't really make the last row much simpler. But you can make this row a little simpler by taking some multiple of this and adding to this to make a 0 in this position. You can't create zeros here and here. Right? So the only thing you can do is do one elementary row operation C to take, what is it? Some multiple of this to add to this to make 0. And then you get what's reduced to low echelon form if you follow that up with scaling to make all the diagonal entries equal to, or the leading entries equal to 1. Okay, so I don't have time to say that, but I will tomorrow at 9 o'clock be very precise about what this reduced row echelon form is. I've sort of hinted at what it is, but I haven't quite stated it very clearly. And you clearly in this example where you have here more variables, then you can't make it upper triangular. You can't make it diagonal. There is no concept. What's a diagonal matrix for a 4 by 3 matrix? Okay. But you can reduce it to this so-called reduced row echelon form. Okay, I will carry on tomorrow. No. Remember the council worker.